Okay, we're going to talk about topic 17C, just a short little discussion of what happens when you do have reactions where they go far enough that you start having a significant backwards reaction. So technically, we're talking about A in a reaction that goes forward and backwards with B. So we can think about the rate of the forward reaction and the rate of the backwards reaction, and we can just write those rate laws. And then we see that dA dt is, so A is changing both a function of how the concentration of A is and the concentration of B, because it's going down if there's a lot of A, and it's going up if there's a lot of B. So we'll have both the term for it decreasing and then the term for the reverse reaction making it increase. So Kr and K prime negative here because it's decreasing in the first step and increasing in the second. So if we start with all A and we don't have any B, then the sum of the two concentrations have to always add up to A0. So we'll use that. And then we can replace concentration of B with A0 minus A so that we can get it into terms of just one concentration. So we'll be able to integrate it. So now the derivative is equal to this expression if we expand this part. And then we can, this is after the integration. Yeah. So this is, okay. So this is the solution. And in order to get there, we're going to, so this is the solution where you can get the concentration of A and the concentration of B, but we had to go back here and integrate it. So in order to integrate that, we just split it up. So took dt to the right-hand side, took everything else to the left-hand side. We're going to integrate from A0 up to A. And I did that in Mathematica. Oops, I think I'll show it on here because on here it's a little bit easier to make it large enough for you to see it. Yeah, so it's just the second one here where we're integrating from A0 to A at some other time. We have our expression that's a function of A, the concentration. A0 is a constant. We have K prime, K forward. So the reverse reaction has a rate constant K prime and the forward reaction Kr. That's all going to be in the denominator, integrate over A, and we get an expression that has a log. But then you want to look at that and realize, if I go back to my drawing, that everything I just integrated on Mathematica then has to be equal to t. So you can rearrange it and raise e to both sides to get rid of the log. So I did check to make sure my Mathematica expression was correct. And you end up with an expression if you solve for A, the concentration of A with time, it will be equal to this exponential function. And so when we think about going towards equilibrium, that's really the point of this little section, is to think about how the concentrations at equilibrium compare to the rate constants. So at equilibrium, if t goes to infinity, so if you go for a long time, you'll reach equilibrium, and then you'll have e to the minus infinity, which is 0. So this second term will go away. So when A is equal to A at equilibrium, this term goes away, and the only one you have in the numerator is Kr prime A0, so this times this, and then the denominator is the same. And then B at equilibrium would just be A0 minus A at equilibrium. And so if we look at this, it's going to be A0 minus this expression. And I tried to show you that that's only in the denominator in this term because it's simply A0 minus A at equilibrium, which is a ratio. So if we rearrange that, so all I did was multiply A0 by the denominator, top and bottom, so that we could get a common denominator. And when I did that, then Kr A0 remains, but Kr prime minus Kr prime 0 cancels each other. And so we end up with B at equilibrium is Kr over Kr plus Kr prime times A0. And then when you take a ratio, so if we look back, let's see, yeah, if we look back, if we take a ratio of our expression for B at equilibrium to A at equilibrium, the denominators cancel and the A0s cancel, and we simply get a ratio of the rate constant forward divided by the rate constant backwards. And so the important thing about this equation for us is that this shows that there's a relationship between equilibrium and the rate constants for the forward and backwards reactions. So we'll use that when we get a little bit further on into our mechanism discussion. So you can also take advantage of this fact that the rate constants are related to the equilibrium constant. And your book talks about some methods called, relaxation methods, where you allow a system to come to equilibrium. And then clearly the rate constants are going to determine the relative rate constants, how quickly you get to equilibrium again. So if you raise the temperature, if the reaction has a non-zero delta H, that's going to disturb the equilibrium. And as it readjusts equilibrium, how fast it does that can give you information on the rate constants. We're not going to use those equations because they're hard to derive and your book doesn't even derive them, but just to know that that's an important method, a relaxation method. So that is all for section or topic 17C.